Welcome to the fifth session on moment distribution method. So in this session we are going to analyze continuous beams with sinking support. So the sign convention what we follow in case of sinking support says if the right support sinks down by delta, then delta is taken as positive. So in this case AB is a member where A is left end and B is the right end. So in this case if B, this right end, sinks down by delta, then in such cases delta is taken as positive. And on the other hand, if the left support sinks down by delta, then delta is taken as negative. So for the same beam AB, if the left support A sinks down by delta, then delta is taken as negative. Okay, that is the sign convention we have to follow in case of sinking supports. Let us consider a continuous beam ABCDE where AB is a overhanging portion and support C sinks down by delta, that is 10 mm. Support C sinks by 10 mm. Okay, so take the value of Young's modulus as 210 GPa and I as 25 into 10 power 6 mm raised to 4. So the first step is to convert the units. So the E is given in GPa and I is given in mm raised to 4. So all other values are expressed in kilonewton and meter. So therefore we have to convert EI into kilonewton and meter. So first E, Young's modulus, is given as 210 GPa. So GPa means gigapascal. So 210 into 10 power 9. Giga means 10 power 9 Newton per meter square. So if you convert it into kilonewton per meter square, so divide this value by 1000. So that means 10 into 10 to the power of minus 3. So 210 into 10 power 9 into 10 power minus 3. So that will be equal to 210 into 10 power 6 kilonewton per meter square. So next value is I. I is expressed in mm raised to 4. So we have to convert it into meters raised to 4. So that will be equal to 25 into 10 power 6 into millimeter. So millimeter, 1 meter is equal to 10 power 3 millimeter. So millimeter is equal to 10 power minus 3 meters. So 10 power minus 3 to the power of 4. So if you simplify it, it will be 25 into 10 power 6 into 10 power minus 12 meters raised to 4. Okay. So this will be equal to 25 into 10 power minus 6 meters raised to 4. So we have converted E and I into kilonewton and meters. So let us take the product of E and I. So E is 210 into 10 power 6 and I is 25 into 10 power minus 6. So that will be equal to 5250 kilonewton meter square. So it is kilonewton per meter square. E is kilonewton per meter square and I value is meters raised to 4. So the product of EI will be kilonewton meter square. So the unit of EI will be kilonewton meter square. So the value is 5250 kilonewton meter square. So this value we are going to use in while calculating the fixed end moments. So next, so it is given that support C sinks down by delta, that delta C is equal to 10 mm. So C is related with BC and CD member. So C sinks down by 10 mm. Okay, so we have to consider this value while calculating the fixed end moments. So the first step is to find the fixed end moments. So let us take the value of EI, which is 5250 kilonewton meter square. So next, the first step is to find the fixed end moment. So before that, because of this overhanging portion, we can directly find the value of MBA. Okay, MBA is equal to, because of the overhanging portion, so this is the overhanging portion AB. AB is subjected to UDL and because of this UDL, the beam, because of the cantilever action, the beam will behave like this, and this overhanging portion will be subjected to hogging bending moment. So if you consider the hogging bending moment, so this is the sign convention to be followed in case of hogging bending moment. So this is left end A and this is written as B. This is A and this is B. So the right end B, at the right end we have a clockwise moment. So that if you apply a clockwise moment at the right end and anti-clockwise moment at the left end, then only you can have a hogging bending moment. That is the sign convention. Okay, so B, in the given problem, B is the right end. So at B we have to apply a clockwise moment. Therefore the direction is clockwise. Therefore the magnitude will be positive. The moment value at BA will be positive. Okay. So what is the magnitude of MBA means? It is subjected to UDL. So intensity into length into half of its length. Okay. So W into L into L by 2. That is the equation to be used to find the moment MBA because of this overhanging portion. So where W is intensity of the loading, L is this 1.5 meter overhanging portion, and L by 2 is half of 1.5. So let us substitute the values. 10 intensity, 1.5 is the overhanging portion, into half of 1.5 is 0.75. That will be equal to 80 kilonewton meter. So next comes is MFBC. So now we have to consider this sinking. Okay. So BC, C is associated with member BC as well as member CD. So we are calculating MFBC, that means we have to consider member BC. So for member BC, B is the left end and C is the right end. So in such cases, delta value should be taken as positive. The sign convention is, if the right end sinks down by delta, then delta is positive. Okay, so first we will find the fixed end moment for the applied loading, and then we will apply the fixed end moment equation for sinking. Okay, so that is because of it is subjected to UDL, we have to use this equation minus WL square by 12. Apart from that, due to sinking, we have to add this extra term. You keep this in mind. We have to add this extra term, that is minus 6 EI delta by L square. So it is minus 6 EI delta by L square. Okay, so 6 EI, we know the value, we have already converted it. Delta, so delta is positive 10 mm. Okay, so because C is the right end for member BC and L is span. Okay, so let us substitute the values of WL square by 12. So W is intensity 10, L is 4 meters, 4 square by 12. Okay, minus 6 EI, 6 into EI is 5250, and delta plus, okay, because this is the right end. Okay, so 10 mm, 10 into 10 power minus 3, that whole thing divided by 4 square. Okay, if you simplify this, it will be minus 33.01 kilonewton meter. That is the fixed end moment for member BC. Next, MFCB. So to find MFCB, same, plus WL square by 12 and minus 6 EI delta by L square. So this will not change. Minus 6 EI delta by L square, it will be constant. Okay, so now let us substitute the values for WL square by 12 as 10 into 4 square by 12, and then minus 6 into 5250 into 10 into 10 power minus 3 by 4 square. Okay, so that will be equal to minus 6.35 kilonewton meter. That is MFCB. So next we will calculate it for MFCD. So next we will move to member CD. To find MFCD, C is the left end and D is the right end. So in such cases, so the sign convention is, if the left support sinks down by delta, then delta is negative. So here for CD member, C is the left support and it is sinking down by delta, then delta is negative. Okay, so that sign convention we have to follow. Apart from that, because of this central point load, we have this equation for WL by 8 and then minus 6 EI delta by L square. So this will be constant. Okay, that will be equal to 50 W, load is 50 into length is 6 meters divided by 8. 50 into 6 by 8, then minus, so you observe here I value is 2i. Okay, so therefore 6 into 2 into EI value is 5250 into delta is negative because it's the left hand. The left hand, if it is sinks down by delta, then delta is negative. So minus 10 into 10 power minus 3 divided by 6 square. Okay, so if you simplify this, the value will be minus 20 kilonewton meter. So next, MFDC. Okay, so MFDC is WL by 8 minus 6 EI delta by L square. So that will be equal to plus 50 into 6 by 8 and then minus 6 into 2 into 5250 into minus 10 into 10 power minus 3 by L square. So the sign convention will be constant for both the ends. It is constant, it is negative for a CD as well as DC, and for BC and CB it will be same. For member BC it is positive and member CD it is negative. That means you have to apply positive for member BC, means while calculating MFBC and MFCB you have to take delta as positive, and in case of member CD delta is negative, means while calculating MFCD as well as MFDC you have to take delta value as negative. Okay, that is the meaning, and if you calculate it you are going to get the value as 55 kilonewton meter. So next, DE is subjected to a central clockwise couple. So therefore MFDE is given by clockwise, means both ends will have positive moments. So M by 4. So MFDE is equal to M by 4. M is the magnitude of the couple, 20 by 4, that will be equal to 5 kilonewton meter. Okay, so if it is subjected to clockwise, MFDE as well as MFED will be positive. If it is subjected to an anti-clockwise moment, then MFDE as well as MFED will be negative. Okay, so at both ends it will have positive. In this case, if it is subjected to an anti-clockwise couple, both ends will have negative fixed end moments. Okay, so MFED is also equal to 5 kilonewton meter. So that is the calculation of fixed end moments. So only thing, in case of sinking supports you have to add this extra term in calculation in calculating fixed end moments, that is minus 6 EI delta by L square. This term has to be added for those members where the joint sinks. Okay, where that joint is associated with those members. For those members only you have to add this extra term while calculating fixed end moments, and for other members no need to apply. So here, since C is sinking down, so it is associated with only BC as well as CD member, and DE does not having any relation or any association with joint C. Therefore we are not applying any 6 EI delta by L square here. Okay, so only the joint which is associated with the members, for those members only you have to apply this extra term minus 6 EI delta by L square. This is the only change you have to consider in the analysis of continuous beams with sinking support. Okay, so next procedure will remain constant. So that is calculation of distribution factors. Same thing. So distribution factors will be calculated for the intermediate joints. So in this case, intermediate joints are C and D. B is not an intermediate joint. Okay, so only C and D you have to find the distribution factors. So the distribution factors are calculated in the form of a table. Joint, first column is joint, member, relative stiffness, total stiffness, and distribution factor. Okay, so for joint C we have member CB and CD, and for member CB the relative stiffness is 3/4 of I by L. Why? Because the far end B is a simple end, therefore the relative stiffness is 3/4 of I by L. substitute the values of I and L, the relative stiffness will be 0.1875 I. Next, for CD member, relative stiffness will be I by L and it will be 2I by 6 because the moment of inertia for CD member is 2I, therefore 2I by 6. So that will be equal to 0.333 I. So the total stiffness is summation of 0.1875 I plus 0.333 I, that will be equal to 0.5205 I. So the distribution factor for CB is the ratio of 0.1875 I to 0.5205 I, that will be equal to 0.36, and that of CD member will be equal to the ratio of 0.333 divided by 0.5205 I. So that will be equal to 0.64. So observe the summation of the distribution factors at any joint will be equal to 1. Next, at joint D we have member DC and DE. So first we will find the relative stiffness for member DC. It is equal to I by L. So that will be equal to 2I by 6, and the relative stiffness for DC will be equal to 0.333 I. Next, for DE member, it is 3/4 of I by L because end E is a simple end, therefore the relative stiffness is 3/4 of I by L. So that will be equal to 3/4 of 1 by 4, that is 0.1875 I. So the total stiffness, again it is 0.5205 I, and the distribution factors will be the same as CD and CB. So for DC it is 0.64 and then for DE it is 0.36. Okay, so that is the calculation of distribution factors. Next, we'll distribute the moments. Okay, so it is distributed in the form of a table. So the first row is joint. So different joints coming under the member are B, C, D and E. So members under each joint are represented in the second row. Under joint B we have member BA and BC, and for member joint C we have CB and CD as the members, and at D, DC and DE, and at E we have member ED. Okay, so next step is to write the distribution factors. Distribution factors are calculated for C and D. So for CB 0.36, CD 0.64, and that for DC 0.64, and DE it is 0.36. Okay, next we have to write the fixed end moment. So MBA is 80 kilonewton and MFBC is minus 33 kilonewton meter. MFCB is minus 6.35, MFCD is minus 20, MFDC is plus 55, MFDE is plus 5, and MFED is also equal to plus 5. So now in this given problem, at end E we have a simple support, and at joint B we have a overhanging portion. So first we will balance joint B as well as joint E. Okay, so let us balance it first. So the first step is balancing of joint B and joint E. So due to the overhanging portion we have the moment of 80. Okay, so this value is fixed. Okay, because of the given loading and overhanging portion, so this moment is fixed, and we know that summation of moments at joint B should be equal to 0. So to make it as 0 we have to apply a moment of 80 minus 33 means 47. Okay, or 46.99. So that this is plus 80 and this is minus 80, then only the joint will get balanced. Okay, so we have to apply a moment of minus 46.99 kilonewton meter at joint B, that means at member BC. Okay, next at E, because it's a simple end, we know that the final bending moment at end E will be 0 because it's a simply supported end. Okay, so to make it as 0 we have to apply, or we have to balance it by applying a moment of minus 5. Okay, so as soon as we apply moments at BC and ED, half of the moments will get carry it to the far ends. Okay, from BC to CB. Half of minus 46.99 is minus 23.495, and half of minus 5 is, that is from ED to DE. It will be carried from ED to DE. Minus 5 is minus 2.5. Okay, so now at this junction we will make a total. Okay, so total at an intermediate junction will be made only in the cases of continuous beams with simple ends, overhanging portions. Okay, so in this given problem we have the combination of both, therefore we are having a total at this junction. Okay, so MBA is 80, MBC is minus 80, MCB is minus 6.35 minus 23.495, that will be equal to minus 29.845, and MCD minus 20, MDC plus 55, and MDE plus 2.5. ED will be 0. So now we have balanced joint E and B. Okay, so now we have left with balancing joint C and joint D. Okay, next go for balancing joint C and joint D. So the imbalancing moment at joint C is both are negative, minus 29.845 minus 20, that will be equal to minus 49.845. Okay, so to make it as 0 we have to apply plus 49.845. So plus 49.845 is distributed among the members meeting at joint C according to the distribution factors. So plus 49.845 into 0.36 will be equal to 17.944, and 49.845 into 0.64 will be equal to 31.9. Okay, so next let's go to joint D. Joint D is applied with 55 plus 2.5, that is 57.5 kilonewton meter. Okay, so plus 57, so to make it as a balanced joint we have to apply minus 57.5. So minus 57.5 into 0.64 will be equal to minus 36.8 kilonewton meter, and minus 57.5 into 0.36 will be equal to minus 20.7. Okay, so that is balancing of joint C and D. So as soon as you apply moments at C and D, half of the moments will be carried from CD to DC, and that from DC to CD. So half of 31.9 from CD to DC will be 15.95, and that from DC to CD, half of minus 36.8 will be equal to minus 18.4. Okay, so these are the carryover moments. You cannot transfer moment from CB to BC and from DE to ED. We have already balanced it. Don't go for balancing again from CB to BC and from DE to ED. Okay, so only you have to balance CD, you have to carry from CD to DC and that from DC to CD. Okay, so next, as soon as the moments are carried from CD to DC and that from DC to CD, the joint C and D gets imbalanced. So we have to again go for balancing. So the imbalancing moment at C is minus 18.4. Therefore balancing moment will be plus 18.4. So plus 18.4 into 0.36 will be equal to 6.624. Then 18.4 into 0.64 will be equal to 11.776. So now the imbalancing moment at D is 15.95. Therefore balancing moment will be minus 15.95. So minus 15.95 into 0.64 will be equal to minus 10.208, and minus 15.95 into 0.36 will be equal to minus 5.742. Okay, so next again we have carryover from CD to DC. So half of 11.776 will be carried from CD to DC, that will be equal to 5.888, and from DC to CD, half of minus 10.208 will be equal to minus 5.104. That is the carryover moments at C and D. Again go for balancing. Okay, So balancing joint C is imbalanced by minus 5.104. Therefore balancing moment will be plus 5.104. So 5.104 into 0.36 will be equal to 1.837, and 5.104 into 0.64 will be equal to 3.266. Now joint D is imbalanced by 5.888. Therefore balancing moment will be minus 5.888. Minus 5.888 into 0.64 will be equal to minus 3.768, and 5.888 into 0.36 will be equal to minus 2.119. So these are the balancing moments. Next step, again it is carrying over from CD to DC. Half of 3.266 will be equal to 1.633, and from DC to CD, half of minus 3.768 will be equal to minus 1.884. So let us carry the last row to the next page. So this is the last row, carry over. So next again we have to balance joint C and joint D. Joint C is imbalanced by minus 1.884. So minus 1.884 into 0.36 will be equal to 0.664, and 1.884 into 0.64 will be equal to 1.18. So imbalancing moment at D is 1.633. Therefore balancing moment will be minus 1.633. Minus 1.633 into 0.64 will be equal to minus 1.055, and minus 1.633 into 0.36 will be equal to minus 0.587. Next again carrying over from CD to DC. So half of 1.18 will be equal to 0.59, and that from DC to CD, half of minus 1.045 will be equal to minus 0.522. Next again go for balancing. So imbalancing moment at C is minus 0.522. Therefore balancing moment will be plus 0.522. So 0.522 into 0.36 will be equal to 0.188, and 0.522 into 0.64 will be equal to 0.334. So imbalancing moment at D is 0.59. Therefore balancing moment will be minus 0.59. So minus 0.59 into 0.64 will be equal to minus 0.377. Minus 0.59 into 0.36 will be equal to minus 0.212. So again next step is carrying over from CD to DC. Half of 0.334 will be equal to 0.167, and DC to CD, half of minus 0.377 will be equal to minus 0.188. So next balancing. Imbalancing moment at C is minus 0.188. Therefore balancing moment will be plus 0.188. So 0.188 into 0.36 will be equal to 0.067, and 0.188 into 0.64 will be equal to 0.12. Next imbalancing moment at D is 0.167. 0.167 into 0.64 will be equal to minus 0.106, and minus 0.167 into 0.36 will be equal to minus 0.06. Okay. So lastly we will final the moments. So final moments are calculated by adding the values from the total under each column. Okay. So final moments, MBA is plus 80, MBC is minus 80, MCB is minus 2.52, MDC plus 2.5, and MCD plus 2.5, DC 26.92, DE minus 26.9, and ED it is 0. So these are the final support moments using which we will find the reactions. So next step is to find the support reactions. Consider each span separately. So let's first consider BC span with the overhanging portion. Okay. So ABC is overhanging. AB is overhanging portion, and total ABC is subjected to UDL of 10 kilonewton per meter. So and moment at CB, MCB is plus 2.52. Therefore, sorry, minus. MCB is minus 2.52. Therefore, it is in anti-clockwise direction. Okay. So, using these, we will find the support reactions by applying sigma Fy is equal to 0. So, that implies Rb plus Vc1 equals 10 into 5.5. 5.5 means 1.5 plus 4, that is 5.5. That will be equal to 55 kilonewton. Next, let us take it as equation 1. Next, let's apply sigma Ma. Take moment of all the forces about A and equate it to 0. So, that implies minus Rb. So, this Rb is inducing anticlockwise moment about A. So, minus Rb into 1.5 and then minus Vc1. So, it is also inducing anticlockwise moment about A. So, therefore, minus Vc1 into 5.5 plus 10 into 5.5 into 5.5 divided by 2 and then this anticlockwise moment of minus 2.52. Equate it to 0. So, if you simplify this, it will be minus 1.5 Rb minus 5.5 Vc1, that is equal to minus 148.73. So, let us, if you rearrange it, it will be 1.5 Rb plus 5.5 Vc1, that is equal to 148.73. Let us take this as equation 2. So, solving these two simultaneous equations, we can obtain Rb as 38.44 kilonewton and Vc1 as 16.56 kilonewton. Okay. Next, let us consider CD member. CD member is subject to a central point load and the end moments are clockwise 2.52 kilonewton MCD and MDC is anti-clockwise. So, this is also clockwise plus 26.92 kilonewton meter. Let us apply the conditions of equilibrium. Sigma Fy is equal to 0, which implies Vc2 plus Vd1 is equal to 50 kilonewton, and take moment of all the forces about C. Sigma MC is equal to 0. So, which implies minus Vd1 into 6 plus 50 into 3. This is inducing clockwise moments. And this clockwise moment of 26.92 plus 26.92 and then plus 2.52. So, if you equate it to 0, you are going to get the value of Vd1 as 29.9 kilonewton. Hence, Vc2 will be 20.1 kilonewton. So, total reaction at C is the summation of Vc1 plus Vc2, which will be equal to 16.56 plus 20.1, that is equal to 36.66 kilonewton. So, next we will consider the last span DE. It is subjected to a moment at the end, at the mid span of 20 kilonewton meter, and MDE is minus 26.9. So, let us apply sigma Fy is equal to 0, which implies Vd2 plus Re is equal to 0 because we don't have any vertical forces, it is a couple. Okay, so therefore Vd2 plus Re will be equal to 0. Next, take moment of all the forces about C, no, it's not C, it should be D. Moment about D and equate it to 0. So that will be minus Re into 4, okay, minus Re into 4 plus this clockwise couple 20 plus 20 and then this minus 26.9. If you equate it to 0, you are going to get the value of Re as minus 1.72. So that means Re is acting in the downward direction. So minus indicates that it is acting in the downward direction. So therefore Vd2 is plus 1.72. So because Vd2 plus Re is 0, so if Re is minus 1.72, then Vd2 will be plus 1.72. So therefore total reaction at D is Rd, which is equal to Vd1 plus Vd2. So that will be equal to 29.9 plus 1.72 will be equal to 31.63. So next we'll plot the shear force diagram. So SFD is plotted by using the applied loads as well as the reactions. So Rb 38.44, RC 36.66, RD 31.63 and RE minus 1.72. Okay. So to draw the shear force diagram, draw the baseline. Okay. Let us start from the left of A. Okay. So shear force to the left of A is 0. Right of A, since it is UDL, we can take it as 0. Okay. Next, shear force to the left of B. Okay, to the left of B we have UDL in between AB. Okay, so therefore the point load, if you convert it into point load, 10 into 1.5. Okay, it is acting in the downward direction, so therefore 10 into 1.5 is 15. So mark it below the baseline for 15 kilonewton. Okay, 10 into 1.5. Okay, so it varies from 0 to 15. Okay. Next, that is the shear force to the left of B. Next, shear force to the right of B is minus 15, and then we have an upward force of 38.44. Therefore, minus 15 plus 38.44, that will be equal to plus 23.44. This is the shear force to the right of B. Next, shear force to the left of C. So, in between BC, again we have UDL. So, we have to deduct it from 23.44. Okay, so 23.44 minus 10 into 4. Okay, so that will be equal to 16.56, minus 16.56. so therefore mark it below the baseline for minus 16.56, and this is the shear force to the left of C. Next, shear force to the right of C is minus 16.56 plus 36.66, that will be equal to plus 20.1. Okay, plus 20.1. Next, let us take this as point F. Okay, if we take it as F, shear force to the left of F, we don't have any force or loads in between right of C to left of F. Therefore, shear force will be constant in between right of C to left of F. Next, shear force to the right of F, we have a downward force of 50 kilonewton. Therefore, plus 20.1 minus 50, that will be equal to minus 29.9 kilonewton. Okay, that is the shear force to the right of F. Next, shear force to the left of D. So, from right of F to left of D, since there are no loading, so shear force will be constant. Next, shear force to the right of D, we have an upward force. Therefore, minus 29.9 plus 31.63, that will be equal to 1.73 plus 1.73. Then right of D to left of E, we don't have any force. This is a couple. Okay, couple is not a vertical force. Okay, so you should not consider this while drawing the shear force diagram. So shear force to the right of D to left of E, there is no loading, so it will be constant. Then shear force to the right of E, we have minus 1.72. So 1.73 minus 1.72, that will be equal to 0. Okay, so this is the shear force diagram. So shear forces above the baseline are positive and shear forces below the baseline are negative. Okay, so this is the shear force diagram. So last, we have to draw BMD and elastic curve. So consider the given beam and then write the support moments as shown here. Okay, so AB, B, because of this overhanging portion, clockwise 80, and BC minus 80 anti-clockwise, and then CB anti-clockwise 2.52, and CD clockwise 2.52, and DC clockwise 26.9, and DE anti-clockwise 26.9. Okay, so use the thumb rules to draw the support moment diagram. So to draw the support moment diagram, draw the baseline first, and the length should be same length as that of the given beam. Use the thumb rules. Okay, so at A it is 0, at BA, so before BA, B is the right end, use the right thumb. So the right thumb is moving in the upward direction, so mark it above the baseline for 80 kilonewton meter. Okay, So since this overhanging portion is subjected to UDL, you have to join this with the parabola. Okay, earlier we used to join with the linearly varying straight line. Okay, so because it is subjected to UDL in the overhanging portion, you have to join with the parabola. Okay, so this variation should be parabola. Next, consider this left hand, left thumb. Again it is moving in the upward direction, so the same point holds good. Next, for CB, C, right hand, right thumb. So here the thumb is moving in the downward direction, so mark it below the baseline. Mark it below the baseline for 2.52. Okay, and join from plus 80 to minus 2.52. Okay. Next, for CD member, C, again left hand, left thumb, again it is moving in the downward direction, so the same points will be holding good. And then at D we have a clockwise moment. Okay, so the right thumb, it is moving in the upward direction, so mark it above the baseline for 26.9 kilonewton meter. So now we have to join from minus 2.52 to 26.9 plus 26.9. Okay, so this is the support moments for CD member. Next, for DE member, D is the left hand. At left hand, left thumb is moving in the upward direction, so the same point of 26.9 can be taken. And at E, the support moment is 0, so join from plus 26.9 to 0. So this is the support moment diagram for the given beam, over which you superimpose with the free bending moment diagram. So AB, because of this loading, we have already drawn it as the parabolic shape. So next we will consider BC member. Because it is subjected to UDL, so the variation will be a parabolic, and the highest ordinate is WL square by 8, which will be equal to 20 kilonewton meter. So 10 into 4 square by 8 will be 20 kilonewton meter. Next, CD member subjected to central point load, therefore the variation of a bending moment is a triangle whose highest magnitude is under the point load, which will be equal to WL by 4, that will be equal to 50 into 6 divided by 4, which will be equal to 75 kilonewton meter. Next, at DE we have a clockwise couple. In that case, the variation of bending moment will be like this. Okay, so you have to consider left and right. Whenever a couple is acting, you have to consider bending moment to the left and bending moment to the right. Okay, so treat this as a simply supported beam. Take bending moment to the left and right of the couple, then you will get the value as m by 2. Okay, so that will be equal to 10 kilonewton meter. Okay, so this is the variation of bending moment diagrams, and these are the points of contraflexure. So, and these are the positive moments, and support moments are negative. Okay, so that is the bending moment diagram. Next, let us draw the elastic curve. To draw the elastic curve, consider the beam without loading. Okay, so sagging bending moment will cause the beam to sag in the downward direction, and negative bending moment will cause the beam to sag in the upward direction. Okay, so this is the variation of elastic curve. Okay, so that is for today's session, and you should know the only change we have to make in case of a sinking support is you have to add this extra term of minus 6 EI delta by L square for that joint and the members which are associated with that joint. Okay, so you have to make only that change, all other procedure remains same. Okay, so that is for today's session. Thank you.